Hello, looks like no one is in the class. Nice. I guess everyone is busy with lab 4.
Yeah, probably.
Okay. Wow. And yeah, I've extended lab 4 deadline. Yeah, I feel sorry for students who have already submitted on time. But yeah, I've extended lab 4 to 2 more days. So now the new deadline is 24th. Uh,
For
that's
students doing Lab 5, would it be possible to push the deadline to probably May 1st, perhaps? Lab 5.
lab 5.
Yeah.
No, because I really want TAs to have some time to grade. So if you put, yeah, if we shift to May 1st, it just puts a lot of effort on TAs because they also have exams, right? Uh, yeah, that's why. Like, I think, but given that Lab 5 has nothing to do with DLXOS, like if
No,
you're
I mean,
taking,
the regular one would be, yeah,
yeah, I mean, we could, but it's just that yeah, TS are pretty busy with their stuff as well. So I really don't want to extend because now Lab 4 and Lab 5 they need to grade them together, right? So which actually puts a lot of effort on them. Like so, unfortunately, yeah, Lab 5 would be hard. Yeah, so I don't think we'll have any extension on Lab 5. I'm sorry. Mm. So, okay, I guess we can start. Like, yeah, before starting, do you guys have any doubts with respect to the course or other topics that we have covered? Yeah, since we are just like four of us, like if you guys have any doubts with respect to projects or like other material that we have covered in the class, this is this is good time to ask. Okay.
Professor, I do have one super quick question,
Mhm.
and it's that the according to the grading policy, it says that there's going to be a 5%
Okay.
allocated for participation,
Mhm.
and at the beginning of the course, it was said that it's going to be posting on Piazza and being generally active. But I'm just wondering if there was any more details you could share with us regarding class participation.
Mostly yeah on Piazza and asking questions on recitation sessions. So I like when I record the session, I usually have logs of everybody who chatted in the session, right? For instance, in the online recitation session, I record each of the sessions, and I also have like chats in which like I see students talk, and I also meet students on in office hours. So I kind of know like how students are doing and like what is the student participation in the class. Yeah.
Okay. Right.
Yeah, I think most of the students would get it just because the way labs are going on. I feel like most of the students, like the lab scores were pretty bad. I mean, I expected lab scores to be good. Lab scores were not that great, so most of the students would get that grade, like would get that points if you're worried about that. Yeah.
Okay. No, it was just out of curiosity. Thank you, Professor.
Okay. So let's start. Uh, so if you guys have like seen like watch the videos, like did anybody watch the videos? Because if you have watched the videos, I could actually go to the most interesting or rather confusing stuff and I can explain the confusing stuff right away, or else I can just start the regular thing. Okay, I'll start the
So,
regular thing. I'll explain quickly, so if you have any doubts please stop me. Okay,
okay.
so yeah, this is the reading for this lecture, but honestly, I don't think you need much of reading because most of the stuff that I covered uh, in the slide should be enough. But yeah, NFS is one of the most commonly used network file system, like sorry, distributed file system, and NFS stands for network file system, without any originality. It's the simplest naming system that they can ever think of, as simple as it goes. NFS, boom, network file system. Very nice. And so it's very widely used today. Most of the file systems that are distributed today are network file systems. One of the main reason for this is its robustness and crash recovery also. Like if the server crashes, it quickly, like when it comes up, there are almost no consistency issues, and it's very robust with respect to like multiple access, concurrent access, everything. It's very robust. Although the performance is not as good as we want it to be, but still it's pretty decent for most of the practical purposes. It's fairly good. Okay, so network file systems here, there will be a client and there is a centralized server called NFS server. So NFS server exposes RPC interface. RPC stands for remote procedure call, so it exposes RPC interface. So clients talk to the server through RPC calls. Okay, and clients could be either Unix or Windows or whatever. Like each client can be running different operating system. So client exposes a uniform interface to the user applications. In case of, if imagine if the client is Unix, so it provides a virtual file system interface, right? The regular file system interface that we see, where you can use all the like regular system calls like open, read, write to access the files. And under the hood, for the file system implementation on the client side, it translates these system calls to RPC calls, which actually send that particular request to the server. And server processes the request and sends back the response, which will be again packed and given as response to the user applications. So in simple words, this is how it works. You have application, we use open, like regular system calls, on kernel, the client on the, so yeah, the file system module on the client side, which runs as maybe a kernel module, that actually performs RPC calls to this file server. Okay, where the file server is the NFS server. So note that there is a translation, right? Like, so according to the application, it is accessing file foo.txt, but when actually kernel sends the request to file server, it will do the translation internally, and it will use this different naming system. Like it uses file handle. Okay, instead of just a file name, it uses file handle. Okay? So the communication interface between kernel and application and kernel and the file server is different, and that translation is handled by the kernel. And this is the beauty of like level of indirection, right? Here the indirection is provided by the kernel, and it it provides this nice transparent access to any files that you want to access, independent of the type of the underlying file system. Applications will always use the same system calls. So another amazing example of how like system problems can be elegantly solved by using indirection. Okay, yeah, so this is how it works on Unix. Like you have VFS interface, depending on the file system that you want to access, you use corresponding module. Like if you have used SSHFS, so you can imagine another module called SSHFS module. So SSHFS, it actually uses Fuse. Fuse is a library that you can use to implement this arbitrary file system. So it's a library that you can use to implement your own file system, and you can install it. And when you install it into the kernel, so kernel will use your library to translate. Like you can use, you can mount your own file system. You can implement the way you want, okay, and mount it in a folder, and then tell to the operating system that this is the library that it has to use to perform all the file operations. Then kernel will actually call those functions whenever any read or write happens under that directory. Okay. Have you guys used Fuse before? Okay, Ragul asked the question, RPC call as in does part? Yes, yes, exactly. Yeah. The regular RPC call. If you have used Java, like in Java, RPC is like pretty famous. So if you have used Java, yeah, regular RPC. So you marshal the arguments, you pack them into TCP, mostly TCP, but few times it could be UDP. You pack them into a UDP packet or TCP packet and then send it to the server. So have you guys ever heard of Fuse before? Like Fuse library?
Not really.
Okay. So Fuse, yeah, Fuse is a library that you can use to implement your own file system very, very quickly. Okay. So yeah. So let's say if you want to, for instance, let's say, yeah, you want to do some things whenever user tries to access certain files in a folder. Okay. Let's say you want to do that, or you want to have a hook for all the like all the calls that tries to access some files under a folder. Fuse library provides you an amazing control that you can use to expose this uniform interface for all the applications. Under the hood, you can do whatever you want. Like if the application calls open on some file foo, you can mimic as if it is reading an HTML web page. Okay, so applications will be now accessing the web page as if they are accessing local files. Okay, you can do that. So that's Fuse. Okay. So NFS design objectives, one is transparent access and fast recovery, and the performance, as I mentioned, it's very reasonable. And naming, so in order for any naming system to be good, or like there are two main properties of naming system: location transparency, location independence. So location transparency is the name of any entity should not reveal its physical location. Okay, and a corollary of that would be the name should not change when the physical location changes, right? So the name should be kind of like independent from the actual place where that entity is located. So NFS provides two ways to access file. So the first way is you can actually use like the server name and then the file. Okay, you can use the entire uh, entire naming, like server name colon the file name. You can use that, or else you can actually use mount to mount the NFS file system, like the one of the folders of NFS file, NFS, yeah, and on NFS server to your local directory, and then you access local directory as if you are accessing like regular file system, and all the communication will happen under the hood. Okay, so you can use either of these two ways in NFS. So a quick example, like if you run, let me share my screen again. So if you say, so on EC grid, you can actually see that NFS, like there are many, for instance, right? Like you see this guy, like the home that we use is usually Dynamo. Yeah, so you see, there's this guy mounted here, which is of like size 8 TB, and that's exactly where my home folder is, right? So there are different files that are mounted. So if you want to see which file system, let's look at perfect. So you see, so here, yeah, we have, this is the NFS file system, which got mount. This is the type here, as you can see, this is the NFS. Okay. So this is the NFS file system, which which mounted on like the home folder. Okay, so all our home folders are actually on NFS file server, that is Dynamo. Okay, so that's why when you do ECN grid, irrespective of the machine on which uh, you log in, you always see your home directory because the home directory is configured as a mount point. Okay. Okay. So basic NFS protocol, it exposes at the lowest most level like six functions. Yeah. So lookup is lookup under a directory. You give the file name and the file handle of the directory under which you want to look up the name, and the return value will be the file handle of the file and then the attributes of the file. Similarly, create will create the file which is given by the name under the directory, and it will return the new file handle of the just created file and the attributes. Removes the file under the directory, so on and so forth. Okay. Note that there is no close and there is no open. The reason is, so you need close and open in order, for instance, like in Linux kernel, you need close and open. Okay. Why do we need close and open in Linux kernel? Why can't we do the same way that we are doing here in Linux kernel?
Those aren't stateless.
Yeah. Okay, good. But what do you mean by that state? Right? Like, what do you mean by Linux file system is stateless?
Well, according to the video, when they're stateless, it just makes it a idempotent, so you don't have to. Um, so like you don't like you could repeat the same operation many times, because if, for example, you add one, so you have like the equation that was shown was like a equals a plus 1. There you'd have to update a, whereas if you do b equals a plus 1, you could do that many times and you wouldn't be changing a.
But why is the Linux file system not stateless, right? Like a Linux file system can also be stateless. You agree?
Mhm. Yeah.
Linux file system is not stateless. Because it uses because you need to do directory traversal every time. Because like, okay, let's assume Linux file system is stateless. Okay, in that
Mhm.
case, if you want to access any file, you always need to pass the like the file name, yeah, the file path, right? Because if you have to read, you need to pass the file path. If you have to write, you again need to pass the file path, so on and so forth.
Mhm.
This actually is inefficient because every time you pass the file path, you need to traverse the directory and then get the inode and do everything. Whereas file descriptor allows you to cache the inode, like directly do the translation. Once you get the file descriptor, that's just an index. Now, given an index, you can quickly get the inode without doing the directory traversal. Okay? That's why Linux file system is stateful, just for efficiency. Okay, it can be
Okay.
stateful, but it maintains state just to be more efficient when it is doing the file operations.
Okay.
Whereas NFS, it is stateless because it provides quick crash recovery. Okay, and so here, in case of Linux kernel or like other operating systems, we use file handle to communicate. In case of NFS, we use sorry. In case of other operating systems, we use file descriptor, whereas in in NFS we use file handle. Okay, so file handle is a unique identifier for that file. Okay. And okay, so the lookup is the first function that NFS supports. It fetches the file handle of the file under the given directory. And now let's say if you have to look up a file list.txt under this directory, so each directory lookup will be translated to corresponding RPC call. which goes to the NFS server, and then so on and so forth. Okay, so the root file handle will be stored by the mount protocol. So if you remember, like we use mount to mount, right? So as part of mount, the file handle for the root folder will be saved. So we always have the root file handle. Then using the root file handle, we get the file handles for the children files. Okay. And when we do, let's say, yeah, here the slide shows how the system calls gets translated to the RPC calls under the hood. The open will be a lookup call to NFS server, and under the hood, we store the mapping from file descriptor to the corresponding file handle, to the NFS file handle. Okay, and we return the file descriptor to the user. And read and write, we again, like when user reads, we get the file handle corresponding to the FD file descriptor, and we perform read, which is the RPC call, which goes to the NFS server, and we read the data into local buffer and copy the buffer to user provided buffer, and then we increment the offset by bytes, and that's it. Note that offset is maintained by the Linux kernel. Like offset is not maintained by the server because server is stateless, so it doesn't know the offset. Whereas offset is for each file, each open file, Linux kernel maintains the offset. So close is just removing the mapping from file descriptor to file handle. Okay, so file handle contains three components. File system ID, this is the ID of the disk partition on which the file system is located. Inode number is the regular inode number. And inode generation number is the generation for this inode. Basically, inode generation number changes every time the inode is reused for some other file. Okay. So like, let's say initially inode generation number will be 0. Once you, let's say, once you delete the inode number, sorry, once you delete the file, then the inode becomes free. Okay. Now let's say you create another file, in which case the inode will be reused. In that case, the generation number for that inode will be incremented. Okay. So when you reuse the same inode number for different files, the generation number keeps on incrementing. Okay. So it is really important that we maintain inode generation number along with inode number, because since the NFS is stateless, inode generation number avoids us in conflicts, especially when you are like when you're trying to access some file, but you are imagining that you are accessing some other file. Like an example is, let's assume that there is no let's assume that there is no inode generation number. Okay, let's say we just have file system ID and inode number as part of our file handle. What can go wrong, right? Let's say the server has the file system ID, which is 12, and the inode number, which is 4367. Client A tries to look up foo.txt, and server promptly returns back the file handle corresponding to foo.txt, which is 12 and 4367. Okay. Now, let's say later, now client A is doing stuff on its machine. Now, let's say client B comes and it deletes foo.txt. Okay, it deletes foo.txt, so the inode becomes free, right? The inode is it's not associated with foo.txt anymore because foo.txt got deleted. Let's say after that, client B tries to create a new file, which is bar.txt, and the file system on the server side, since 4367 is free, it will use the same inode which just got freed, and it will assign to bar.txt. Okay. Now, let's say client A tries to read, assuming that this belongs to foo.txt, right? Because when client A accessed, it did belong to foo.txt. And now let's say client A tries to read. Client A thinks it is reading foo.txt, but actually it is reading bar.txt. So this is the problem if you don't have a generation number. Ragul asked, does it maintain a table for this? Yes, yeah. So yeah, so like if you have a generation number, then the generation number would have changed here. So, but the generation number would be different here. So when client A tries to read, server can say, hey, sorry, the file doesn't exist anymore, right? That way client can actually detect errors. Okay? If there is no generation number, there is no way that client, like the uh, asynchrony that happens can never be detected. Okay, unless like client A asked for the file name and like ask for foo.txt later again, there is no way for client A to know that somebody deleted foo.txt. Okay? So stateless design also provides good crash recovery because, for instance, let's say, okay, when crash happens, let's say the server crashes. Okay, what the server has to do? It just needs to reboot. That's it. Everything will be fine. Now, what does client has to do? Client has to do nothing. It just sends a request and it will wait. If the server responds, it uh, it gets the data, or else it can just wait. Because nothing, there is no state maintained by the server for each client. So server doesn't need to do any recovery or like any client state recovery, right? Server is fine. Client is even unaware of NFS server crashing. So client is so dumb that it doesn't even know that server crashed, because for every request it is like it sends all the data that is needed for every request. So client is even unaware of any crashes happening on the server side. So the stateless mechanism provides very nice crash recovery mechanism.
And Vidush asked the question, is there a limit to the generation numbers? How many times I know when the reuse since it must be fixed?
Yeah, Vidush, yes. There is a, yeah, of course, there is a limit, right? Yeah, the generation number will be of fixed width size. Yes, there could be, the loop over can happen. You are right. The loop over can happen, especially when you quickly delete and uh, like when you quickly like delete and restore, like create another file, it can quickly happen. Yes. But most often when it tries to happen, I think that's a, well, it also depends on how NFS server uses these generation numbers, right? And also it also depends on how client uses the file handle. For instance, like here in this case, right? Imagine client A, okay? So one way that client can avoid using, like client A can avoid this problem is every time it needs to read, okay, it always gets the file handle, fresh file handle. It always does the lookup. Okay, that's one way client can avoid having this problem, right? Instead of just saving the file handle, it can, every time it tries to read, it can always look up and get the fresh file handle for foo.txt. That way it can prevent uh, like this loop over.
The question, is there any security risks here?
Yeah, I mean, so one security risk is this one, right? Not exactly security risk, but more of like inconsistency issues. Like you could basically, one client can make other client think that it is reading some file, but it is reading some other file. Okay, basically in uh, in like if you think more deeply, if client A is using the file to execute, you can have another client B doing an arbitrary code execution on client A by just repeatedly uh, deleting the file, right? Repeatedly deleting the file, recreating the file, deleting the file, recreating the file. And let's say client B gets lucky and it manages to create some other file with the same inode number, then it can actually make client A load arbitrary code, because client A thinks that it is running ls, but maybe it is running some code that is controlled by client B, right? So it can happen. Yeah, it can happen. That could be one thing that that can happen.
Is it possible for a hacker to create a loop for delete and reuse coming?
Yeah, you can do that. You can do that. Honestly, like I don't have much idea about NFS. So if you delete the file at such a rapid rate, you could actually make cause the generation numbers to go overboard. And but since generation numbers are only are like specific to INO number, so it doesn't matter, right? Sure, you wrap around and you come back and you get the old generation number. Generation number starts from 0. So that's actually an interesting question. So yeah, I don't know. Maybe it's possible. Yeah, that's actually a very interesting question. Yeah, something that since NFS is you have ECN grid that uses NFS, you can try to experiment this with ECN grid. But yeah, but don't do it now because already ECN grid is experiencing some heavy heavy loads. That's why like temp got crashed earlier this weekend. So yeah, you can do it after the semester. Yeah,
He can also ask Chad.
yeah, exactly. Oh, can this be asked in finals? I don't know. I don't know. Oh, yeah, I mean, the answer is pretty tricky, right? I mean, any answer, by giving any answer, I'm revealing some information. So I don't know is a good answer. The information gain is 0. Okay, so uh, we have looked at stateless server and why stateless is good. Crash recovery is amazing. So it has reasonable performance because you almost, since like one way to achieve good performance is of course by caching, right? The traditional good old method of caching. So that's why client-side caching is a commonly used mechanism where client actually caches some data that is present on the server. Like the famous cache for file systems is the page cache. Here, like the client maintains cache for all the data blocks that are read by the user applications, and the writes usually happens in a write through manner for metadata, but for data blocks it's usually write back. And caching also avoids kind of amortizes slow network. If you have a very slow network, then it's better to use caching rather than every time communicating with the server. That's why if you have noticed accessing, like if you have used your for your lab, if you have used SSHFS and mounted the temp folder on your machine and try to work using VS Code, that is actually that you feel to be much faster than doing VI on the server itself and trying to access the files. If you have done both cases, you could actually see a noticeable performance difference. Okay, so how does caching happens? So yeah, okay. Another problem with caching is consistency. So how to keep data consistent between client and server, and how to keep data consistent between clients. So a file could be changed on the server, like the thing that I've just shown before. So will client see any update? It depends on the read policy on the client, because it depends on how client caches, right? Similarly, if a file gets written on, let's say a file is being used by 2 different clients, and let's say one client writes to a file, will other client see the write? It depends on the write policy on client side. So if the client doesn't propagate writes to the server, there is no way other client can see the update. So yeah, we can have serious inconsistent states. For instance, we can have 2 different copies of the data on 2 different clients, whereas the copy that is on the server could be completely different from either of these clients. Okay. So the commonly used mechanism for reads to maintain cache consistency for reads is we maintain two caches, attribute cache and data cache. So attribute cache is the cache for the file attributes like file handle and file attributes, right? And data cache is the cache for all the data blocks of a file. Okay. So attribute cache can be used to determine if the file changed. Okay. So if the file changed, then the attributes change. That means the data could have changed. We don't know which data have changed, but we just know that data has changed. So that's why if you see any changes in the attribute cache, then you just discard all the data blocks that you have cached for the reads. Okay. Now, how to update attribute cache? So attribute cache will be updated every n seconds. So there is a time, let's say n equal to 60. So after every 60 seconds, we always update the attribute cache. So basically there is a time to live field for each attribute. So whenever the time to live expires, TTL expires, we refetch that attribute, okay? And we also refetch the attribute when some user applications tries to open the file. So let's say when user application tries to open a file, we see the timestamp on the attribute that we have cached. If the timestamp is 3 seconds, like older than 3 seconds, we just refetch that attributes from the server. Okay.
So just to be sure, when we're working on a file, there are two caches: the data cache and the attribute cache. And the attribute cache we don't touch, we don't see, and that's one essentially going to be running in the background, such that every t seconds, like whatever is configured, it's going to fetch the data again.
Right.
And if it sees inconsistencies, it drops the data cache.
Exactly. It drops all the blocks of that particular file.
Okay, thank you.
And the update of the attribute cache happens, can happen in two scenarios. One, the time has expired, that like in 60 seconds has expired, or when some application is trying to open the file. Okay, when an application tries to open the file, we see that the attribute is actually fresh. How do we check the attribute is fresh? We see the last fetch date of that attribute. If it is last fetch time of that attribute, if it is older than 3 seconds, then we just refetch that attribute. Perfect. So let's see an example. So here, let's say client A, we have a client has file A attributes and blocks 1, 2, 3 cached. So now let's say client opens file A, the attributes is cached. Okay, now let's say client tries to read block 1. Where does it get the block 1 from? Cache or server? Anyone? Where does client reads block 1 from? From cache, right? Because it's cached. Correct. Let's say after 70 seconds. Perfect. Yeah. Let's say after 70 seconds. Now let's say client tries to read block 2. Where does it get it from? Okay. So that's not true. We only get the file attributes from the server, right? Since the file attributes did not change, we don't discard block 2. So block 2 will still be from the cache.
Okay, from the data cache.
Exactly.
Okay.
Good. Now, let's say block 3 is changed on the server. Okay, the data block 3 of file A is changed on the server. Okay, let's say here, now let's say client tries to read block 3. Where does it get it from? Anyone?
If it's changed, then it does pull it from the server, no?
No, only block 3 changed on the server, but there is but the client doesn't know that block 3 changed, right?
Mm-hmm.
So, and 70 seconds is like within 70 seconds. So 70 seconds has expired. So we are still in that period of 70 seconds. So it still gets the block from the cache. However, it gets the old value.
But it would lead to an inconsistency.
Yes, 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 of course.
Okay, okay, that was okay.
It will still get the old value. And now let's say now when client tries to read block 4, where does it get it from? So block 4 will get it from server because block 4 is not present in the cache. Okay. Now let's say client waits 70 seconds again, 70 seconds expires. Now client refetches the file attributes. It sees that file attributes got changed. Okay. At this point, all the data blocks, that is blocks 1, 2, 3, and 4 will be dropped. Because note that we just fetched from block 4 from the server, and block 4 is also cached. So we will, at this point, we will drop all 4 blocks. Okay. Then here, when client tries to read block 3 and block 1, so it, of course, it gets it from the server. Okay. Any questions on read consistency? Okay, good. So the writes happen in similar manner, but the only difference is writes to the directories are write through. That means they will always be committed to the server. So whenever you write to any directory, it will always go to the server. Okay. For file writes, write back happens every 30 seconds. Or basically every 30 seconds, we just flush the data blocks that we have just written to the server. Okay. Or if the user application that has access to the file, if it closes, then we will do the flush. Okay. By flush, I mean like pushing the updates to the server. Okay. So here in this case, again, let's look at an example. So here, let's say we have client X and Y that have open file A, which has 3 blocks, blocks 1, 2, and 3. All 3 are cached. So now let's say client X writes to blocks 1 and 2. Okay. Now client Y, when it tries to read block 1, it gets the old value because client X hasn't updated the server, right? So client Y gets the block from its cache. Say after 30 seconds later, client Y pushes the updates. Client Y reads block 2. Sorry, client Y it's client Y which reads block 2. What happens? It will read from cache. It will get the old value. Note that client X already pushed the data to the server, okay? Because 30 seconds expired. I think I did not add the thing, but 30 seconds expired. So at this point, after 30 seconds expired, client X pushed the new blocks 1 and 2 to the server, okay? But client Y has no idea about the update, correct? So when client Y tries to read block 2, since block 2 is cached, it will get the old value. Now let's say 40 seconds later, so the total time is now 70 seconds. Here, client Y now refetches the attributes for file A, right? And client Y notices that the attributes changed. Okay. Now it will actually drop the blocks 1, 2, and 3. Now when client Y tries to read block 1, it will get from server. Similarly, if it tries to read any of the blocks, it always gets from the server. So any questions here? So here it's actually a bit it could be a bit confusing because we are mixing, like, so there are 2 things at play here in case of write consistency, right? We need to consider both the time for the like attribute cache, which is 70 seconds, and also the time for write updates. For instance, here, like every 30 seconds, all the writes will be pushed to the server. So after 30 seconds, like client X actually pushes writes to the server, but here after 70 seconds, now the attribute cache on client Y change will be different. So client Y now drops all the blocks. So it could be a bit confusing, but if you think about it, it's fairly easy. Like you need to, like the attribute cache is the main thing here. Once the attribute cache changes, that's when all the, like either the changes to the data blocks, yeah, basically all the cache will be the data cat. Sorry, the data blocks, the cache for the data blocks will be affected by the attribute cache. So we just need to monitor when the attribute cache changes. That's it. So any doubts here?
So is there a way to flush the cache entries?
I mean, yeah, so you can always do a flush, right? I think the way when you do a flush on a file, you can do flush like syncs is called on Linux. So if it is an NFS file that you have just opened, it'll do a flush to the NFS server. Okay, so in conclusions, distributed file systems are cool, but the only distributed file system that's of relevance that is used most commonly, like in servers, are NFS. So like NFS is the only file system that you should really worry about. Honestly, the right, like now at this point, people are working like the consistency here. The main problem is consistency, right? Like we are getting old value, like everything. There are many problems that you can imagine that could happen, but in reality things are even more messier than this. So especially like if you are using cloud systems, let's say Google Cloud or Amazon AWS, so there you have this, Amazon provides, I think, elastic storage. Okay, so there the disks are located somewhere else, and the consistency they use is they use this term called eventual consistency. So they cannot promise you any like any time limit. Here, at least we know that after 70 seconds, we will definitely see an update, right? At least we know for sure here in case of NFS. Whereas in certain file systems that are used on cloud frameworks, they call it eventual consistency. Basically, you will get an update, but there is no limit. Eventually, maybe after 1 hour, maybe after, I don't know, maybe after a couple of hours, you may get an update. That's why, like when you see, uh, especially like if you have, if you are on YouTube, for instance, even when you delete a file, but the file or like delete a video, the video could be viewed in some regions up to some point. The video doesn't get immediately deleted, by the way. So like somebody can still view that video because the updates, you think that the when we do like delete on the file, it gets deleted, but no, the file gets cached at so many levels in reality. So in order to have a consistent update across all the systems where that file is cached, yeah, it's a nightmare. It's really a big thing. It's, all the like even Cloudflare, like almost all the cloud based infrastructures have this huge consistency problem, and one thing that they don't provide is consistency. They actually give up consistency for performance. Okay, that's basically it. So yeah, these topics are actually kind of old. I mean, in reality, things that happen are like way messier, and most of the times you don't, like distributed file systems are kind of like they don't hold much value now, especially like when you have hierarchical databases, like especially when you have databases. So the file systems are like now people are using databases instead of file systems. Okay, honestly, databases replace these distributed file systems so well that instead of using distributed file systems, we just use databases, and databases kind of provide the similar infrastructure, especially for web services, which most of our applications are. So, I mean, none of the applications that we use are local applications. And at least the ones that actually do some work, right? None of them are local applications. Everything has a web component. So, and if you have a web component, then yeah.
So is there a way to flush? Okay, I think that's on.
Okay. So, any other questions?
No, thank you very much, Professor. Have a great day.
Okay, you too. Bye. Hey, Vidush. Hey, okay.
Oh, hey, Professor. Yeah, I was waiting for
Oh, hey, what's up?
I think you're still recording, by the way.
Oh, okay, I'm sorry. Oh, wow, okay, shit. Oh, wow, yeah, my entire screen is shared. Wow, you guys should, damn. Did you guys see anything bad?
No, I didn't. I didn't see. I turned my face the other way.
No, it's fine. Let me stop sharing. This is so messy.